This is lesson 5.1.2, Gravity and Applications. So Sir Isaac Newton, while thinking about the moon, he figured that there had to be a net force acting on the moon, because if that were not the case, due to his first law of inertia, the moon should be moving in a straight line. But because it's moving in an orbit fashion around the Earth, there had to be a force acting on the moon, a net force acting on the moon. That's how he came up with gravity. And he didn't call it gravity, it was called the Universal Law of Gravitation. Okay? Let's write down what it says. So the Universal Law of Gravitation says, every particle or object in the universe attracts every other particle or object with a force along a line joining them. Such force is called gravitational force or gravity. All right. So that means any and every two particles or objects in the universe attract each other. Okay? That sounds crazy and silly, but it's true. Meaning that any object around you feels attracted to you as much as you're attracted to it. Again, sounds weird, but it's true. Okay? Mathematically correct. All right. So let's say we have two objects. It could be planets, particles, whatever you want. Okay? We have this one and this one. Let me move it a little bit so that it's easier to find the line joining them. Okay, so then we have to find the center of mass. I know we haven't talked about it, but the center of mass for most objects in our class will be at the center. And then between any 2 points, you can always draw a straight line. So that's the line joining them. Meaning that the force will act along that line. Okay? Because this one is a bigger object, we are going to assume it has a bigger mass. So this is capital M. The smaller mass will be lowercase m. And then let's define the distance between them. Okay? So the distance between them from here to here, we will call r. Okay? Distance between them, we'll call it r. So that means there's a force that way because mass capital M feels attracted to mass lowercase m. In the same manner as this mass is attracted to the bigger mass. Okay? That's the gravitational force. All right. So let's see the mathematical implications of Newton's universal law of gravitation. The formula goes as follows. This formula says the gravitational force or gravity is equal to capital G, that is the universal constant or universal gravitational constant, universal constant of gravitation. It has many names, so people just call it big G. I call it universal constant. Multiplied by the product of the masses, that is mass 1 or one of the masses times the other one, divided by the distance between them squared, divided by r squared. Okay? This constant has a value as follows. 6.673 times 10 to the negative 11 Newton times meter squared per kilogram squared. I know the units get weird, and that's because constants have to yield a certain unit. So these units are in such a way that when you use the formula, you end up with newtons because it's a force. Okay? And then this is the first mass, the second mass, and then the distance squared. So let's think about the mathematical implications of this one, the proportionalities. So let's write it again. I'm leaving that much space on purpose. So let's say if one or both of the masses were to increase, it doesn't matter which one, as long as one increases, as long as the combined mass is bigger, then that means the force will increase. Likewise, if the masses get smaller, then that means the force will decrease. Okay? That one's a direct proportionality. And if the distance between them increases, then that means that the force decreases. So when two things are far away, they feel almost no force. There's no attraction. Some people say that's why long-distance relationships don't work, because if you increase the distance, the attraction decreases. In the same manner, if the distance between them decreases, then the force increases. This is the same thing as magnets. Well, not the same thing, but it works mathematically the same way as magnets. Once they're closer together, there's more attraction between them. What that means is distance and force have an inverse relationship. Okay? So distance and force, I misspelled and, are inversely proportional. If one goes up, the other one goes down. Okay? And this is something called the inverse square law. Okay? Many things in physics were with this one, but just as a side note, this is an example of inverse square law. Okay. So I remember before I was a teacher, I saw an image and I found it online, and it was really cringy. So first of all, we know that this is apocryphal. This probably did not happen. And I want you to look at the arrows that represent vectors. These arrows kind of suggest that the apple is attracted to the earth more than the earth is attracted to the apple. You might be saying, well, that's the case, right? No, that's not the case. Because we have Newton's third law of motion, which says for every action force, there's an equal and opposite reaction force. So, although it seems crazy, the attraction or the force with which the apple attracts the earth is the same as the force with which the earth attracts the apple, because for every action there's an equal and opposite reaction. I know this seems crazy, but once you work out the mathematics, you end up thinking of acceleration, okay? So because this is a very small mass, the acceleration it experiences toward the earth is larger when compared to the acceleration that the earth feels toward the apple. Because the earth is very massive, the acceleration it feels toward the apple is so small that it's practically zero. But it's still there nonetheless. Okay, so this is wrong, completely wrong. In fact, let's do a big X. This doesn't work. The force felt by the apple is the same force as the force felt by the earth. Okay? And then we can see it over here. My arrows had the same length, although this mass was smaller. Okay? Just to show you, let's write it down, okay? So, as per Newton's third law, all force pairs are equal and opposite. Okay? Don't forget. So that means when you fall down, the earth is attracted to you as much as you are to it. Okay. So there's a simulation from PhET that I want to show you. If I can get it to load. So I couldn't get it to load, but here it is. And what I want you to notice is force on M1 by M2, this arrow. Force on M2 by N1, this arrow. Again, it's very, very, very small. The force is very small. But this is just to show the relationship we talked about, right? That when they are closer together, the force should increase. So let's try that out. They are. They increase. The number is increasing. And likewise, when I get them far, the force decreases. Okay? And I want you to see which one has more impact. So let's go back to here, okay? If I get them closer, very quickly I get, over twice the force. However, let me get them back. If I make this twice the mass, I did not get twice the force. So decreasing the distance, or the distance just by itself, just the distance, has more impact on the force than the mass. Although the mass has impact, right? It does increase. Decreasing the distance makes the force way bigger than just increasing the mass. Okay? So for instance, very, very, very strong force. If I move them a little bit, decreases. But if I decrease the mass, the rate at which the arrow decreases is less than that. Okay, less than that. And I can use scientific notation. That's the way we'll use it, right? There you go. You can see it. It's a little bit better. So, there you go. That's the simulation. Now I want to talk about lowercase g, acceleration of gravity. Everyone knows it. It's 9.8. Where does it come from? Well, let's see. We know that every object in the not in the universe, on planet Earth, falls at the same rate, at 9.8 meters per second squared. So let's think of you or me, okay? Let's find the force of gravity, the gravitational force we experience because of the Earth, all right? That is our weight. So we know that, let's use mine, okay? So my mass is 75 kilograms. That is my mass. Okay? So that means I am attracted to the Earth in this way. So my weight, the force of gravity, is equal to my weight. My weight is mass. I know it's normally g, but let's just say it's an acceleration, right? I'm accelerated toward the center of the Earth. Let's call it acceleration of gravity, a sub g. Well, because I am on planet Earth, I am a mass, or I have mass, so does the planet. I can apply Newton's Universal Law of Gravitation, because as we said, every two objects or particles are attracted to each other. So g times the mass of the Earth times my mass divided by the distance, the radius of the Earth squared. Why do we use the radius of the Earth? Because the center of mass of the Earth is in the center. In the center of mass between me and the Earth, it's closer to the Earth, but yeah, so that's the line that joins me and the Earth. A line, imaginary line going from about my belly button, more or less, towards the center of the Earth, okay? So we use the radius of the Earth. All right, so notice how my mass is irrelevant because it cancels. So the acceleration at which I would fall toward the center of the Earth is simply universal constant times the mass of the Earth divided by the radius of the Earth squared. So we plug in those numbers, we'll have 6.673 times 10 to the negative 11. Let me move my formula over here. Newtons times meter squared per kilogram squared times the mass of the Earth. I have it over here. 5.97 times 10 to the 24th kilograms divided by the radius of the Earth squared, which is over here. I think that was for the 6th power? Yeah. And then I have to square this quantity. Let's use decimals. So we'll start with the universal constant. 6.673 times 10 to the negative 11 times 5.97 times 10 raised to the 24th power, 6.37 times 10 raised to the 6th power, and don't forget to square this one, 9.81. So then the acceleration numerically is about, let's just round, right? About 9.81 times, not times 10, 9.81. And then when you cancel the units, you're going to get meters per second squared. And that's where it comes from. So it doesn't matter what object is falling on the Earth because the mass cancels. That's why when we covered kinematics, the mass is irrelevant to gravity. Mathematically, it cancels. That's it.